Okay, so I'll talk about microstate geometries and the mechanism in which they have to hover above the horizon. This is work in progress with these people. The people in blue are going to come to California. Bert is coming to Stanford for 6 months, and Andrea is coming to Santa Barbara. So if you have more questions, you can ask them more details. Those people are in the market this year, so remember their names when you look at postdoc files. I'll try to. I don't know if I will succeed, but I'll try not to mention the word fuzzball in the talk. So I'll see how far I can get along. So there's an old story by Strominger and Waffa, which actually counted black hole microstates back in '96. And if you count black hole microstates, you can actually match the black hole entropy on the money. You can actually match the Bekenstein-Hawking entropy. But then there's another question which one can ask. Once you do the Strominger-Waffa matching, you can ask if you take one particular microstate. I don't want to look at all of them. I don't want to look at the whole ensemble and everything. I just want to look at one of them. And to follow that microstate as I increase G string from weak coupling, where it's described by some bunch of strings and branes, to strong coupling, where again you count the entropy of the black hole. And there has been a standard lure by Susskind and then Horowitz-Polchinski, and with more details by Damore-Veneziano, that as gravity becomes stronger, the brane configuration becomes smaller. Makes sense, gravity pulls things together. On the other hand, the black hole horizon becomes bigger. As we all know, black hole horizons grow when gravity becomes stronger. And at some point, which is called the Horowitz-Polchinski correspondence point, the horizon comes up and engulfs the black hole and engulfs this thing, and then you end up with the standard black hole. That has been the story for all for black hole microstates. However, what we have been discovering is that some of these microstates, some of these Strominger-Waffa microstates, at least for some particular black holes, have no intention of doing that. Rather, when you go to strong coupling, when you increase G string, they go to something which looks like a black hole from far away, has the same throat, but doesn't have a horizon. It actually has some smooth ending, some smooth cap. And the big question, in my opinion, is, is it possible that actually all the black hole microstates, all the things which describe the black hole microstates are actually given by such configurations? And this is basically what Matur put forth in 2003 as a conjecture. For some reasons, it got labeled as a fuzzball conjecture, which, again, I don't like the word too much. But the question is, is it true that, the black hole really is given by such horizonless microstates? And, if you want to make an analogy with an ideal gas, in an ideal gas, you have thermodynamics. You can describe the ideal gas by thermodynamics, PV equals nRT, and so on and so forth. Or you can describe it using statistical mechanics. You can describe the ideal gas using, microstates, which are like, typical and atypical, molecules zooming around at 200 kilometers an hour. And the same would be in the black hole solution. In the black hole, when you have a real black hole, you would have a thermodynamic description, which is given by the black hole classical solution from the textbook, which describes the physics very well far away. But it breaks down at the horizon, where you basically have this statistical description, which is in terms of these microstate horizonless geometries. And the horizon, the scale of the horizon would be like the mean free path when you go from thermodynamics to statistical physics. If you are talking at the scale of a meter, you can trust fluid mechanics in the room. If you go to the scale of the mean free path, you'll have molecules hitting you back and forth, and you don't have any more fluid mechanics description. So in that sense, the way I understand this, conjecture is that we are trying to replace the classical black hole solution by something which takes over the physics at the horizon, and therefore the classical black hole solution stops describing the physics at the horizon. Other ways of putting it, thermodynamics, effective field theory breaks down at the horizon. There will be some new low mass degrees of freedom kicking in, which actually destroy this low energy, effective field theory. Other ways of putting it is that there's no space-time in star black holes. You have just some quantum superpositional microstate geometries. If you think about in ADS-CFT language, you basically have on the boundary some states, and you have the ensemble. The ensemble is described by the black hole. If you want to ask any thermodynamic question, you should use this thermodynamic description that's captured by the black hole. If you want to compute, macroscopic quantities, if you care about one particular states, they're actually given by those. And again, this idea of replacing the black hole and basically by this configuration, yes.
Does states necessarily mean energy eigenstates?
In the supersymmetric thing where I'm looking at, there I have a very clear understanding. The states are just d1, d5 by fundamentals carrying some momentum in some quantum state. Those are all zero energy states.
But how much attention is being given to the question, how different is the basis of definite geometry and the basis of definite energy?
In the supersymmetry case, it has to be the same because everything is at zero energy. When you go far from supersymmetry, it's hard to argue. I mean, I'll move, in the whole talk, I'll go in the supersymmetry case, and then I'll stretch a lot to just go, 1 millimeter away from supersymmetry.
Okay.
And then, then maybe we can ask the question at that point. In the supersymmetry case, it's a clear correspondence. You have the energy, everything has zero energy on one side, zero energy on the other one, and at least in the two-charge case, which you understand. The geometries form coherent. They describe coherent states, and they actually form a basis to span the Hilbert space of everybody and their brother. There's some discussion about supergravity breaking down and them being described by some stringy configurations. But in the two-charge case, the states actually give you a basis for the geometries give you a basis to span your Hilbert space.
But by the time you get to Schwarzschild, you do expect the dynamics to be chaotic, which sort of implies a maximal difference between the energy eigenstate basis and any other basis, any basis.
Can you postpone it until
Sure.
I'll try to have some speculation about Schwarzschild, but that's step by step. So again, at least for supersymmetric examples, this is something which can be discussed in string theory, can be proven or disproven in string theory. But there's a word of caution, and this is something which basically Gary Horowitz bit me into my head. When Samir had his conjecture back in 2003, I was visiting Santa Barbara. I was a postdoc at UCLA, and Gary said, but these ideas have been along for a while. Everybody and their brother has been trying to replace the black hole by something to resolve the information paradox. But you cannot do that. You cannot just replace the black hole, put something there. First of all, whatever you put there falls in. And then second, even if you do it, even if let's say you get some Grava star, or some people have something which obeys some equations of motion, which stays at the horizon, which stays horizon sized, the moment you increase G string, the moment you increase the Newton constant, the black hole horizon becomes bigger, and whatever you build using quarks and matter and electrons and waves and stuff becomes smaller and actually falls in. So even if you do it in your theory for some particular value of G string, for G string equals 0.17, the moment you make it 0.18, you have made the black hole bigger, and you don't have something to be horizon sized. So if you want to replace the black hole by some animal of any sort, it should have the same growth with G Newton as the black hole horizon. And that's a very stringent test. That's a very stringent test which I don't think any of the things which people people have proposed to replace the black hole with do. And I'll show you that in a bit in the future how this black hole microstate geometries actually pass the test. It's quite a non-trivial mechanism. So how do we build these solutions? This is work which we did about almost 10 years ago. We're taking the Strominger-Vafa black hole, which is a 3-charge supersymmetric black hole. This is the workhorse of all string theory calculations about black holes. This is the first one you attack. And we're trying to find some solutions which have the same charge as this black hole, which have the same mass as the black hole, but don't have a horizon. And the way to do it is actually to replace. This solution is actually a 5-dimensional solution. It has time and has an R4. And the way to do it is to actually replace the R4 base by some 4-dimensional hyperkähler space, which is, for example, which can be a Gibbons-Hawking space or a top-knot space. These spaces have a fiber, have a harmonic function V, which basically multiplies the fiber, and the fiber shrinks at various locations. So if you just replace this R4 base by some hyperkähler manifold, you basically have to solve 3 layers of equations. This equation for a self-dual 2 form, this equation, and and whatever solution you get actually has black hole charges, and looks like a black hole from far away. Now notice that this system of equations, this and this and this and this, is a linear system. Meaning you first solve for these fields, you then use this result to basically solve this equation, and then use this result to solve this linear equation. So in a sense, you are solving linear equations once you know the hyperkähler solution, which is a very nice thing. It implies that these solutions can be found with some ease. It's not so hard to, it's not as hard as just solving some horrible second-order coupled equations, and that's again because you have supersymmetry. And even when you have a top-knot base, actually the solutions can be found even easier. They are given in terms of 8 harmonic functions. And the general solution basically has a top-knot base which has some cycles, which has some top-knot centers, which can be distributed in any way you want. Once you have the top-knot centers, those centers actually near each of the top-knot centers, as you well know, the geometry looks like R4. There's no singularity in the geometry. So this solution, which has multiple top-knot centers, is actually going to be smooth. But it has a non-trivial topology because at each top-knot center, the top-knot fiber shrinks to 0. As you see from here, this function V has a pole. And when the function V has a pole, the fiber psi shrinks. And because the fiber psi shrinks, you basically have a 2-cycle running between each two centers. You have many two cycles in this problem. And you can actually go ahead and put these 8 harmonic functions and do a bit of work. Okay, it took us about two years to figure this out. And then you're actually going to find lots and lots of solutions which have the same mass and charge and size as the black hole, but have no horizon. And the way these solutions are realized is actually you'll have many two cycles, and these cycles have on them magnetic flux. Again, I showed you there's a two form which is self-dual, and this form gives you magnetic flux. Now, as it has been known in string theory for quite a while, when you have two magnetic fluxes and you have an F-wedge term in your action, you can have two magnetic fluxes sourcing for you an electric field, behaving like an electric charge. When you have two magnetic fluxes which have opposite legs, they actually can behave like an electric charge. So you're getting the black hole charge not from some singular electron points. You're getting the black hole charge from these magnetic fluxes crossed into each other, which again sources this this electric field for you. You can ask, where is the black hole mass? Well, the black hole mass comes again from the energy of this field, of this electric field. Where's the black hole angular momentum? There's an E cross B term which gives you angular momentum, and this is, again, you have terms of the form electric times the magnetic field, and this gives you angular momentum. So you can actually get all the black hole information, both the charge and the mass and the angular momentum, by looking at these geometries, which actually don't have any singularities, which don't have any horizons. And those geometries are like bubbling geometries. They are very similar. Those of you who are familiar with the LLM story, that's exactly what you have there. You have the solutions which have bubbles, which have no singularities, and they actually are the ones which describe the physics. There's a similar thing which happens in Polchinski-Strasser if you back react, but nobody has done it yet. Essentially, you basically replace the singular centers by bubbling geometries. You actually have some bubbling, and those bubbling geometries, if you think about them from a GR perspective, they would be black hole solitons. That's what people call black hole solitons. There have been some theorems in 4 dimensions from ages ago, from Cambridge, saying that there are no solitons without horizons. But recently, Gibbons and Warner have actually argued that actually these theorems only work in 4-dimensional gravity. If you're in 5 dimensions, you actually have either no solitons without horizons or no solitons without topology. And this is one example in which, again, this no solitons without horizon theorem is evaded, and you actually have instead no solitons without topology. And again, you're getting all these black hole solitons, all these black hole-like solutions with no horizon from having topology. And again, those of you who are familiar with flux compactification and Klebanov-Strasser, that's very similar to Klebanov-Strasser. There are no singular sources, or the charge is coming from the fluxes. So that's the story. Any questions? This is the main ingredient of these solutions. Yes, so if you take the solutions, which are, again, M-theory solutions, if you compactify them down into type 2A, you basically have each Gibbons-Hawking center becomes a D6 brane. So these solutions actually become D6, D6, D6 bar, multi-center solutions. And Denef actually had constructed those solutions, long before us. But, he didn't think about uplifting them. And, essentially, there's a story. We connected at some point with this Denef multi-center for dissolution story. So, again, all these solutions, if you compactify them and you look at the limit when type 2A theory is valid, they actually become singular D6 branes. But once you uplift them in M theory, they become smooth. And you actually get this multiple D6 is just, lifting up to some topologically non-trivial structure. Yes, so these solutions you can actually put these Gibbons-Hawking centers whenever you want. So in principle, there's a moduli space which has dimension 2n minus 2. When you have n centers, there are basically 3n positions which you can put. There's a center of mass, you get 3 of them out, and then there are some equations which you call the bubble equations. People call them the Denef equations, which actually tell you that the positions of the center must satisfy their n minus 1 equations, which must be satisfied to avoid closed timeline curves. And then once you take those into account, you find that the solution which has n centers has actually 2n minus 2 continuous parameters. And then you can actually ask, can you quantize those continuous parameters? And you can. I'll go on the next. I'll discuss it on the next slide. Okay. So now the question is, those solutions are nice, and as one was saying, they have continuous parameters. However, if you try to count them, if you try to ask how many solutions are there, you'll find that you are nowhere near the black hole entropy. The black hole has an entropy which is actually quite large, which goes like Q1, Q2, Q3 to the power 3/2, and if you try to quantize these solutions, you don't get anything like that. So the first thing which you can try to do is to actually combine the knowledge of the two-charge system, where you could actually get the entropy from supergravity solutions, with these bubbling three-charge solutions. Those are three-charge solutions. They have the black hole charges. In the two-charge case, people were able to get some entropy, and the way they got the entropy was by using some object called the supertube. A supertube is some object which is a supersymmetric brane configuration, which can have arbitrary shape, and yet preserve supersymmetry. This is not something which you'll find if you read Joe's book. In Joe's book, you'll find that if you put branes at an angles, the angles have to have some special relations. However, when you pile together 4 types of d-branes on top of each other, you can arrange by being sneaky that the densities of the d-branes basically go, they change as they go along the tube in some way, and the killing spinors of this configuration actually remain the same, even if this d-brane turns and goes back and forth and swashes and so on and so forth. You can arrange that the killing spinors of this configuration actually always remain the same all the way through, and therefore this configuration is supersymmetric. It's a pretty subtle game, but it works. And Juan and Oleg and Samir and Liad Maoz, ages ago, they actually found a solution in the D-only-5P, in the D-only-5 frame. They found a solution corresponding to the supertubes in flat space, and actually found that this solution, again, has arbitrary shapes, is supersymmetric, and moreover is smooth in the D-only-5 frame. Now, what we tried to do is to take the supertubes, which can have arbitrary shape, and put them into these bubbling geometries, put them into these three-charge geometries, and ask, can we get some three-charge solutions, which again look like a black hole, they look like the Strominger-Vafa black hole from far away, and they have these supertubes inside. Of course, having supertubes, you get much more entropy, because the supertube depends on a continuous function. So if you ask what's the dimension of the moduli space, classically it's infinite. It depends on an infinite number of parameters. So you should definitely get more entropy from supertubes than from just having centers which move around. Otherwise, putting it, the supertubes basically they depend on the M-theory direction. They actually break the UN invariance along the M-theory direction, and therefore, since they break one U1 extra, there should be more of them. And if you do that, again, it has been quite a painful thing to do. One can construct the supertubes, and you need Taub-Green's functions. It's a pretty gory mess. But once you do that, what you find is that, first of all, the supertube solution is smooth if you put it in this background, exactly like in flat space. And the entropy which you get from the supertubes goes like q to the 5/2 to the power 1/2. So that's still not, so again, this comes because you have supertubes which are wiggling, and they're wiggling inside this very long throat, and inside this bubbling solution. One thing which is good, if you look at these solutions and if you look at this entropy, there have been some papers by Jan de Boer and Shearer Schauk and Messamach and Dieter van den Bleeken asking that, saying that supergravity has a limit in entropy. There's a limit of how much entropy can be in classical supergravity solutions. Well, the point is they're only counted solutions which have this U1 invariance. The moment you break the U1 invariance, you actually get more entropy. So, for example, these bounds, if you actually look at the supertubes, you are getting more entropy than these bounds have. These solutions again have an extra broken U1. However, this solution is not black hole-like. We are not getting the black hole entropy. If you just put if you just put a single supertube, you don't get the black hole entropy. We are getting close. Before we were at q to the power 1/2. Now we went from 1 to the power. We went from q squared to the 5/2. We gained the factor of q in the power, but we are still not nearby. However, those are all fully backreacted solutions. Just to boast. Those are all fully backreacted solutions. So there's quite a bit of them. Then, actually, Don Marolf, ages ago, he actually wrote a paper with Belkis Palmer where he quantized supertubes. And I remember he told me that if you want to get the black hole-like entropy, having supertubes which have functions of one variable is not going to be enough. And back then, I didn't understand too much. But then, actually, looking backwards, indeed, this is actually what's happening. There's a limitation. And the point is the following: if you look at the supertube and you count the entropy, you are counting some. The supertube has 8 shape modes. And it depends again on 8 functions of one variable. And when you count the entropy, there's some Cardi-like formula. Square root of C times L. C is 8 and L is some occupation number. And if you just look at L, how much L is, you find that L cannot go bigger than q to the 5/2. It cannot get bigger than that, otherwise you get closed Semi curves. Then we actually started to look with Jan de Boer and Masaki Shigemori and Nick, which we started to look at some object which may depend on 2 variables. And what we argued was the following. As I was telling you before, if you look at supertubes and you ask why Joe's book doesn't have them, the reason is that they have actually 2 d-braining. They actually have 4 types of d-brains on top of each other, and the supertubes actually can preserve the same supersymmetry regardless of orientation. So I can take a supertube bit which goes like this, another one which goes like this, another one which goes like this, another one which goes like this. They have the same supersymmetry. And then I can glue them into getting this thing which has an arbitrary shape. Now, what we argued was that there should exist another object, which we call the superstratum, which is even more complicated, which has about 8 ingredients. KK monopole charge here, and here, and here, and D1 here, and D1 here, and D5 here, and D5 here. Pretty gory god-awful stuff, which has a projector. Now, supertubes actually, if you look locally, they have 16 supersymmetries. Each bit of the supertube, each chunk of the supertube has 16 supersymmetries. When you put them together, the 16 here and the 16 here are not the same, but only 8 of them are the same as you go along the supertube. And then the full wiggly supertube has 8 supersymmetries. Here we found a similar object. We found some horrible mess which has 16 supersymmetries locally. And if you bend it in one direction and you try to glue it together, and you only look at shape modes in one direction, you find that you actually get 8 supersymmetries. If you put it in the other direction and you glue it in the other direction, you're going to get 8 supersymmetries. But nobody stops you from gluing it both this way and this way. And therefore this object, this piece of tube, which actually has 16 supersymmetries, can be glued into some object which in principle depends on function of 2 variables. And this is something which we label the superstratum. So again, if you take a normal D1, D5 system, a normal D1, D5 system can oscillate in the transverse direction, and those are again the Lunin-Matur and the Lunin-Malsana-Maus geometries. They oscillate. They have an isometry along the common D1, D5 direction, but they actually have a shape mode in this direction. If on the other hand you take a D1P configuration and the D5P, if you put a momentum on the D1 and the D5, they actually start wiggling. They get a mode along the common D1 direction, along the common D1, D5 direction. And what you can show is that by a supertube transition, you can go from here into something like this, or you can go from here into something like this, and this is going to be the more generic object. So what we did, again, we took a piece of this guy, and then we zoomed in and we said this guy has 16 supersymmetries. If you make it into something which depends only on this direction, it will have 8. If you make it into something which depends only on this one, it will have 8. But generically, it will have 60. It will have only 4. Yes?
So in the end, is this two-dimensional? Is this an arbitrary two-dimensional surface?
Yes. That's what we hope. So from this gluing argument, again, in the supertube case, what can you do? You can say, let's take a supertube bit, and then let's take another supertube bit, and then, let's glue them. Each supertube bit has 16 supersymmetries. There are 8 which are common. There are 8 supersymmetries which don't depend on how the supertube bit gets oriented. And therefore, when I glue them, I'll get an object which depends on an arbitrary functions of one variable. That's the supertube story. Now, if I take the same logic and I extrapolate it, of course, in the supertube case, you also have a Born-Infant description, you also have a supergravity description, so you have many other arguments that the supertube exists, except this one. Now, if you take the same logic and say, can I find a piece of junk in string theory which has 16 supersymmetries, but however, if I bend it in this way and in this way, it preserves 4 and 4. It has 4 supersymmetries which are independent on how it bends. Then I expect to be able to build an object which depends on function of 2 variables, which actually then can look like this. That has been our argument. Again, we don't have, I'll show on the next slide. And we call this a superstratum because, essentially they have this, strata towers in Dubai. I think this was the concept and this is the actual building which came out. So, I hope it will not be the same in our case. It will not. This is much uglier. This was nice and beautiful. This one, it's okay, but, still. This one would have been much nicer. So I hope it will not be as bad for our thing. Yes. Which will get by quantizing. I'll show you in a second. How it works. So again, classically, this solution should depend on function of 2 variables. So there should be an infinite number of functions of 1 variable. So, and each function of 1 variable has an infinite number of classical parameters. So you should get gazillions of solutions, and then once you quantize, hopefully things will work. So what do we want? We want smooth solutions which depends on functions of 2 variables. Now, if you call the Gibbons-Hawking fiber of this, of these solutions of this Gibbons-Hawking base psi, and you call the D1-5 common direction V, the solutions found by Juan and Lunin and Oleg and Samir and Liad Maoz, they actually depend on the function psi. They actually depend, and so again, you can think about those solutions as having an R3 base, and then you have 2 U1 fibers, V and psi, and you have time. So the solutions which they found depend on psi, but don't depend on V. They are V independent. Now, what you can do, since you have, again, an R3 and 2 fibers, and the time, you can actually flip the fibers. You can just call the V fiber psi and the psi fiber V. Nothing stops you from doing that. And then you'll get from those solutions some V-dependent solutions, which, again, are the same as those, but I'm just rewriting V, I'm just relabeling V and psi. And then what Ben Niehoff and Nick Warner did was to find a more general configuration which has functions of psi and another function of V. They are different functions, but they're two functions of different variables. The big thing in this game is to actually find a function which depends on two variables, psi and V, and that's what we're trying to do right now with Masaki Shigemori and Nick and Ben. We're trying to find whether one can construct this solution. It's, again, a pretty gory solution. Imagine, depends on two variables and so on. But I'm optimistic it's going to work. I mean, we have pretty serious arguments that it should work, and we're trying to find it out right now. However, one can do something more. So once you have the solution, even before one has the solution, one can ask how much entropy do these animals have? How much entropy can you get from by quantizing their shapes? And then what you can argue is the following: if you look at the dimension of a single supertube, again, classically it's an infinite dimension, you can have any shape it wants. But quantum mechanically, once you quantize those shapes, you can find that the dimension of the moduli space is actually given by 4 times and 1 times and 5. And then if you look at the MSW, the Sennett-Strominger-Witten counting of the M5, M5, M5 momentum black hole, the dimension of the moduli space of the M5 ring gives you the number of momentum carriers. So if you assume that this guy exists, again, we haven't built the solution yet. I don't have a Born-Infeld description, but again, I only have this argument based on projectors that it exists. If you assume the object exists and comes from putting momentum modes on supertubes, the moduli space dimension of the supertube is actually going to be 4 times and 1 times and 5, and this is going to give me the number of momentum carriers. And if you count again these momentum carriers and add the fermions, you'll get on the nose the Strominger-Vafa entropy. So if this object exists, again, we don't have it yet, it's not something, I could declare that it exists and so on. I have strong arguments it exists based on both my Kinning-Spinner arguments and the supergravity solution, but I don't have it yet. If it exists, on the other hand, if I quantize in this way, I can actually quantize again LMSW and I can get the Strominger-Vafa entropy on the nose. Yes, you had a question. Yes. So first of all, I want to quantize. So the supertube quantization, which one can get easily from the Marlow-Palmer paper, for example, that's quite easy to do. So you look at the supertube with no momentum, and you can ask what's the dimension of the moduli space, and that's going to come out as 4 times and 1 times and 5. Actually, it comes out to be 8 and 1 and 5 because you also have torus modes. But then, so at the beginning we thought, gosh, we are getting more entropy. But then what's happening if you look at the superstrata degrees of freedom? The superstrata only happen when you have wiggles when the torus is intact. So actually, the superstrata degrees of freedom cannot carry momentum and preserve supersymmetry. So that's basically the story. So again, the dimension of the moduli space is 4 and 1 and 5, and this gives you how many momentum carriers you have, and you get in the 2 charge again. You are getting the 3 charge black hole entropy basically on the money with the right 2 pi in front. So that's something which it was quite pleasant to see because again we've been trying for all these years to get the entropy, and I think this is the route to go. So the story for BPS microstates is that we have a huge number of fully back-reacted ones. Again, I have q to the 5 quarters fully back-reacted solutions, which I can put down, I can write down on papers. They depend on continuous functions. They are smooth, and if this superstrata exists, which again I'm pretty sure it exists, it actually gives me the Strominger-Vafa entropy on the nose with all the right factors. So that's actually that's one thing. You can also argue, and this is something which is much more complicated using mass gaps and using long throats, that the mass gap of this configuration is the same as the mass gap of the guys which live in the typical sector of the dual CFT, and therefore, and this is where the black hole states live as well. So you can argue using mass gaps and arguments like this that the microstate solutions which we are constructing, they also have they live in the same sector as the black hole microstates. And then there are also 2 other calculations, basically one by yes. No, it's not e to the minus n. This is a supersymmetric black hole, so the gap is 1 over n1 times n5. I'm still doing supersymmetric. Again, bear with me. I'm slow. So solutions. The only thing, I'll get to Schwarzschild. I'll get to Schwarzschild and mass gap calculations and things like that. I'll get to them a bit later. But so far I'm doing supersymmetric. The mass gap is 1 over n1 times n5. It's just you have a CFT. There's a long effective string. The length is n1 times n5, and the mass gap is 1 over that. That's the It's a pretty simple thing. Now, there are two non-backtracking calculations which are done in 4 dimensions, and which argue that one can get a black hole entropy by looking at scaling multi-center configurations. Which, again, if you turn on back reaction, they actually correspond to this. They actually correspond to these microstate solutions. One of them is again using something called black hole deconstruction by Denevgato, Strominger, Van den Blecken, and Yin. And there's another one which actually we call a Higgs Coulomb map. That's something which I did in collaboration with Micha Berkutz and Cyril Schauk and Dieter Van den Blecken, and also Li Wang and Yi had a similar paper soon after. And the story for supersymmetric BPS microstate seems to be the following. When you go from Strominger-Vafa and you look at, you count the entropy at 0 coupling, and then you increase the coupling, make the coupling bigger and bigger and bigger, and at some value of the coupling, this is described by this multi-center quiver quantum mechanics, and you can find that, essentially the black hole entropy comes from big things which don't have a horizon, which actually grow with this string. You go at some other value of the coupling a bit further out, which again, this is not full back reaction, and there you can also get the black hole entropy on the nodes from things which are, again, becoming bigger and growing. And then you go to the full back-reacted regime where the black hole exists, and you find these microstate geometries, which, again, have superstrata and stuff, and essentially, they also don't have a horizon. So the punchline is that for supersymmetric black holes, the typical states grow as Gn increases, the horizon never forms. And therefore, we can think about, what's wrong about the supersymmetric solution. You basically have the singularity, and you have quantum effects from the singularity, which go all the way to the horizon, and just completely invalidate the classical, the classical geometry. Yes.
Do you have an argument that you can't put one of your superstrata inside one of your n-centered, backgrounds and get even more entropy?
If I can build it in flat space, I'm pretty sure it's going to work in the n-center. I don't need to put it actually. This counting argument.
No, I know you don't have to, but I'm worried that you're going to get more than you want. I mean, could you, if your superstrata exists and have the entropy that you want in flat space,
once
you have an argument that you cannot then find solutions in which they are then embedded in an n-centered background and you get even more states than you...
Essentially, there are 2 different ways in which superstrata and bubbling solutions carry momentum. The superstrata carry momentum by becoming V-dependent. So, if you look at the superstratum and you ask, how, and you put momentum on, so you have the D1E5 common direction, which is V, and the superstratum carries momentum by having wiggles on the V direction, by having waves on the V direction. A bubbling solution carries momentum by having fluxes of one type and fluxes of another type, which actually give me the momentum charge. In a sense, I have I have an F12 time and F12 and then because of those, I'm sourcing GT3, which falls like 1 over R to some power at infinity, which is the momentum. So the bubbling solutions are V independent, and they carry the momentum. The superstrata, in a sense, they are V dependent and carry the momentum. So they have different ways of carrying momentum. For a long time, I believe that the things are, these bubbling solutions which you have are going to be it. There will be the building block. But right now with the superstrata, again, I'm getting the entropy, so that should be the right thing. Yes.
Yeah, to answer the same question, since the bubbling solutions, the old-fashioned ones, since they have a lower entropy scaling, then there shouldn't really be any issue with sticking a superstratum into the same thing, because the bubbling background will be subleading anyway.
Just a quick question. So you're really just solving classical equations. I guess so in that sense they aren't really quantum, although there are quantization conditions on the flux. But
yes. No, but there are also quantization conditions on the moduli space. So if you look at the moduli space, classically it has infinite dimensions. So if I look classically, I'm just getting an infinite entropy. If I just do MSW and then look at the dimension, it's infinite. But then I can quantize these geometries in a sense. Okay, the way to do it is to go to the Marov-Palmer picture where you have supertubes, and then you look at the field theory on the supertubes, you quantize that one, and you're getting the quantization of the geometry from this auxiliary theory. There's another way of doing it, which Jan de Boer and people in Amsterdam have done, which is actually to quantize multi-center solutions and so on, which is to quantize directly in geometries. But those are the two different ways of quantizing. And there's no. So again, this is the story for supersymmetric ones, and then for non-supersymmetric extremal solutions, we also have a huge story. We have many solutions. They are much harder to find. They are not. You don't have any supersymmetry to help you. But because you have extremal solutions, somehow the equations factorize, and somehow life becomes much nicer. So this is something which we are doing with. I've done with Andrea and Orestes and Nick Warner and people in Europe. We've been trying to find solutions which are non-supersymmetric but extremal, and basically the same story goes. The same story holds. So that's the story for extremal solutions. Now people always ask the question, why do you want to destroy the horizon? The horizon has low curvature. I can go to there drinking my coffee. What's the mechanism for destroying the horizon? And the answer is, the answer which I always tell is that, in this example, the space-time solution has a singularity. It happens to be behind the horizon, but, I don't have any Bible telling me that, because the singularity is behind the horizon, it should be holier than singularities which don't have a horizon. And when you have a singularity, we know from many examples of string theory that you may have low mass degrees of freedom coming from the singularity and changing your physics on a large distance. And that's something which is very common in string theory. This is, what's happening in Boczynski's thruster. This is what happens for giant gravitons. You have singularities which, look to be, basically the curvature only grows inside 1 centimeter cube region of space. And you can say, great, I can stay 1 kilometer away from there and I can do physics. And the point is, no, you cannot. Because the singularity can have low mass degrees of freedom, which can come in and screw up your space-time on 1 kilometer scale. So this is really the mechanism which string theory has. Whenever you have a singularity, the singularity basically can wipe out your solution on a long distance if it has low mass degrees of freedom. And in this particular case, we do have this mechanism, and the mechanism seems to be, it basically has 3 incarnations. If you think about, the level of the solutions, you basically have topology and fluxes, which is the same as bubbling geometries. But then you can actually imagine turning off, making these cycles very small. When you make the cycles very small, these bubbling solutions actually, they become polarized branes, very much like you see for giant gravitons, and very much like we see in. So when you have giant gravitons, you have the LLM geometries, which are bubbling geometries. If you make the cycles very small, they actually become polarized branes. They actually become momentum modes polarized into diffee branes. And then if you make the size even smaller, if you make the coupling constant even smaller, there's a way to describe those things using non-abelian degrees of freedom. So again, the mechanism behind the existence of those things is basically some combinations. It's the same mechanism, but it has 3 incarnations in basically 3 different regimes of parameter. You can either call it non-abelian or brane polarization or bubbling. It depends on how big your charges are and how big your G-string is. And I want to emphasize that these effects, these effects which wipe out the singularity, can actually be present even when you don't have a singularity. Now, if you say, okay, singularity resolution, black holes have singular, they are bad, this effect, wipe out the horizon. But there are some geometries. There are some geometries which are basically these bubbling geometries which have a long throat. And you can actually quantize them. You can actually quantize, basically, you can quantize these solutions, and you can argue that quantum mechanically, these solutions which have very, very long throats are not there. They are actually excluded. So you can actually have quantum effects wiping out classical geometries. Those are classical geometries with low G-string, with low curvature. Everything is nice and under control. If you look at the solution classically, it makes perfect sense. However, you can have quantum effects coming and wiping it. Essentially just wiping out these 2 solutions. And that's happening because you are approaching the region where the black hole is. None of those things is a black hole. The black hole has an infinite throat. None of those things is a black hole, and yet quantum effects come and wipe it out. So that's basically the mechanism which works. Now, of course, we're doing BPS black holes, which are extremal, and the horizon, again, is a causal feature of the singularity. And again, we're seeing that this singularity is resolved by stringent low mass modes. So, this is the Penrose diagram. That's the naive solution, the classical textbook solution. That's what we are getting. We are getting these solutions, which start different from each other at the horizon scale. But then people who do black holes for a living and people who do GR, they tell us, big deal. I have known this for ages. Everybody and their brother knows that extremal black holes, they're unstable. The horizon is unstable. You can get garbage coming all the way to the singularity. That's something which people knew. So what's the big deal? The big deal it's about the non-extremal black hole. When you look at the non-extremal black hole, you can ask, how does this story extend? One option is that in the non-extremal black hole, you also have the singularity, and you resolve it on the scale of the inner horizon. And that's logically possible. That's a logically possible extension of what I'm saying. However, the big deal about Samir's argument and about amps is that this singularity doesn't get resolved on that scale. It gets resolved all the way to the outer horizon. There's garbage which happens all the way to the outer horizon. So the really big deal about these proposals and the fuzzball proposal and this firewall argument is that when you go to the horizon, that's the singularity resolution scale. It's not here. It's not here. It's actually here. And if you look at the classical solution, it's actually backwards in time. It's before the solution. It's before the singularity forms. And this is the really big deal about all this, about Samir's proposal and about AMPs. Now, of course, the idea you don't want to actually build solutions. You'd actually like to just go here and just do the same story, repeat song and dance, just build lots and lots of solutions and count them and get the right number and then declare victory. However, this is not easy at all. Essentially, you have second order PDEs, which again are non-coupled and they are non-linear, and they do not factorize in any way. So there's no way to get them. We've been trying for many years to build something, but essentially we gave up. There's an old Romanian proverb: "Not to pray to the saint who doesn't help you." It really doesn't work. We really tried, and it doesn't work. And then essentially we had this idea to actually be a bit sneaky and to look at near-extremal. And when you have near-extremal solutions, there's a way to get near-extremal solutions by taking one anti-D-brane. So again, you have some D-brane charge in the fluxes, and you can take anti-D-branes and you can actually put them in as probes. And you can argue that these anti-D-branes make some sense. And this has been done by Katru, Pearson, and Verlinde, in the Kleber-Strasser solution. They actually took anti-D-branes in backgrounds which have charges in the fluxes. And what we did with Andrea and Verknock was to take supertubes, which have negative charge, which have opposite charge to that of the background, and to actually put them in the solution. And what we found is that the supertubes have metastable minima. And moreover, they can decay to supersymmetric minima by brane flux annihilation. Essentially, you have the charge which is negative, and there's a charge in the flux which is positive. There's a tunneling, and actually they can annihilate. And this actually gives you Hawking radiation. So these metastable supertubes give you microstates of near-extremal black holes. This is one example. So you take this long throat solution, which has some bubbles here, and then you put a supertube at one of those things, and then you can actually look at the potential of the supertube, and you can see that if you zoom in this part of the potential, you can see metastable minima here. Here, there's a supersymmetric minimum here. If you go to this place, there's another metastable minimum here. There's another one here. And then there's another supersymmetric minimum here. So you really have many metastable vacua. You have many metastable minima for supertubes in these backgrounds. Yes?
When you say this gives Hawking radiation, I mean, what's been checked? Is it the same rate?
No. This is just words. So the point is, this decays. So these metastable vacua can decay, and when they decay, they can emit, some, there's an energy. This energy gets emitted. They go to the supersymmetric state. So this is like a near-extremal black hole, which actually emits its non-extremality, and just goes to non-extremal. The rate is very small. I mean, you expect the rate to be exponentially small. There's unfortunately not too much literature. Actually, people have not done too much work on on understanding near-extremal black holes and how they Hawking radiate their last quanta. How they go to absolute zero. How can this happen? If anybody knows some literature and this is some place where one can check rates. One can check what's the decay rate and how does it go with the charges and so on.
Well, there are very old arguments that back reaction becomes important in that limit, and in fact that was one of the motivations for these very old 1+1 dimensional models, the CGHS model. Mm-hmm. That's a simple model of a near-extremal black hole. Mm-hmm.
Yeah, here in a sense, the back reaction, those things again, they have they have a very tiny amount of non-extremality, and when you emit this photon, the photon just goes out. So in a sense, it's not the black hole eating up a photon and becoming non-extremal. It's rather the black hole being the microstate being non-extremal, spitting out the photon and becoming extremal. And I think the rates are exponentially small. I remember from Per Krauss, his paper with Wilczek, but I'm not 100% sure. So if you look at these near-extremal black hole microstates, you can ask, how do they look like? And what we could do actually is to get some microstates which they have some length throat, and we could get some which are bigger and some which are smaller. So if you look at the black hole and the horizon is at some depth, we could get very easily solutions and microstates. Some of them are shorter than the black hole, some of them are longer than the black hole. And then you can actually compute the force. You can actually compute the force on a probe D-brane, which these solutions exert. And this is done, the way KKLMMT compute the force on a probe D-brane in flux compactifications is not a hard calculation. And what you find is that this probe D-brane actually experiences wild fluctuations. Essentially, if the metastable minimum, first of all, if the solution is longer and shorter, you can get the probe to be the same. But then if the solution hops from, one metastable minimum to another one, this force actually varies wildly. It can actually go from positive to negative. It can really it really has a lot of fluctuations. So if you look at the probe D-brane from far away, at least these metastable minima which are constructing, which again, I'm not saying they're typical, I'm not saying anything about how, but they're the only ones we have right now, they actually seem to have very wildly fluctuating force. They exert a very wildly fluctuating force on an incoming D-brane, on an incoming probe. And it looks like, I'm pretty sure that, that incoming probe feels the difference between, microstate 1 and microstate 2. Microstate 1 attracts it, microstate 2 repels it. So, that should feel the difference. Now, so again, at least for near-extremal, the big deal seems to be that, this singularity, which again, you have this Penrose diagram, you have this singularity. For near-extremal, at least, these solutions that you have, they resolve the singularity all the way to here, all the way to the outer horizon. So then the question is, what's the mechanism? Again, people have been arguing, what's the mechanism for resolving the singularity? Essentially, the mechanism is really, you have topological cycles which have opposite fluxes. Again, if you backtrack the supertubes, you can actually find that you have some fluxes, some cycles. In the supersymmetric case, all the cycles, all the fluxes have positive charge, and the charge is equal to the mass. In this metastable supertube case, what's happening is that in some region you have positive flux, you have positive charge in the fluxes. In some region you have negative charge in the fluxes, and overall the charge is lower than the mass. The mass adds up, and the charge actually subtracts. And essentially these solutions, again, they actually have non-trivial topology. They are black hole solitons, and they have, again, regions of positive and negative charge. Gibbons and Warner, in their recent paper, they have argued that if you want to get anything which has black hole charge and is stationary, the only way to get it is like this. The only way to get a stationary solution which has black hole charge is to actually have topology and fluxes. There is no other way. You cannot have, Mickey Mouse going around and, giving you these configurations. If you want the thing to be stationary, this is the only thing which is possible. That's again shown in this Gibbons-Warner paper, and this is one example to basically build these things. So the mechanism for keeping this again is basically bubbling, or again in some other regime is brane polarization. Some branes which again want to become big, and again in some other regime this brane polarization can be understood as some non-abelian effects on some branes. This is the mechanism why these things work, and this is very similar to flux compactifications. There are some papers by Ganagic, Beam, Vafa, Freivogel, Schmidt, which actually discuss flux compactifications which have regions which have negative charge and regions which have positive charge. Again, they don't find a full back reaction and so on and so forth, but they argue that this kind of flux compactification should be present. The story here is the same, it's just that you have three charges and the equations are a bit more complicated, but it's really the same story. You have some manifold with some topology. In some region the charge is positive, in some region the charge is negative. Now, what about other black holes? The point is, we have done these near-extremal black holes, but if I give you this Penrose diagram and I ask you this is the Penrose diagram of what? And the point is, it can be the Penrose diagram of near-extremal black holes, or it can be the Penrose diagram of a Schwarzschild black hole with one electron. It's exactly the same Penrose diagram. If there's no rotation, it's exactly the same Penrose diagram. And as a result, once you know that string theory resolves black hole singularities backwards in time, again, we know this for the near-extremal solution, the question is, why wouldn't it do it for the other solution? Once I have one example that in string theory, these kind of singularities get resolved backwards in time all the way to here, why would it stop at near-extremal? Why would it stop from, maybe, there's some vicious reason and, why it should stop, or some sadistic reason why string theory should stop doing that. But if it does it once, if it does it in one example, in one circumstance, why would it stop all the way to why would it stop from not going all the way to Schwarzschild plus one electron? And then the question, to answer Joe's question, what's the mechanism? Is it the same mechanism, or maybe it's something more complicated or smarter or so on? At least in the near-extremal case, I could get metastable configurations by having bubbles with flux which have opposite charges. When you go to Schwarzschild, you can argue that the generic microstate should be chaotic, or the generic microstate should be time dependent. Those things I don't know. But at least in the near-extremal case, it looks like the building blocks are just fluxes and charges which are opposite to one another in different regions of the space. And the mechanism keeping this from collapsing is again topology and fluxes. That's the mechanism which, that's why this thing doesn't collapse into a black hole and the horizon doesn't form. It's because of this topology and fluxes. So, and of course, once you go to Schwarzschild plus 1 electron, you can just take the electron away and you can get to Schwarzschild. You can be even more vicious and you can say, okay, I have a Schwarzschild solution which has a space-like singularity, gets resolved by quantum effects backwards in time. What about cosmological singularities? Why stop at Schwarzschild? But again, those are words. I don't have any equations to put on them. So my global vision of what's going on is that at this point there are two efforts. There are basically two directions of attacking this problem. We're all trying to find out that typical states differ from black hole solutions at the horizon. This is what Samir has argued using information theory arguments and generic idea CFT, which doesn't involve d-branes or solutions or anything. Just generic idea CFT. And in this approach of which is just information theory arguments, one can be agnostic of what's the underlying theory. ADS-CFT can be a generic feature. All conformal theories which have some operators of some dimensions could be mimicked by some ADS background. So ADS-CFT may be just a way to rewrite conformal field theories in some smart way. And one can be agnostic about where this happens, in what theory this happens. And one can argue that generically at the horizon you will have these large fluctuations, wiping you out. But the problem is, this constitutes black hole hair at the horizon. This is really, if you want to put a firewall there or if you want to put anything there, this is black hole hair at the horizon, and you need a mechanism to prevent the collapse. Unless one has such a mechanism, essentially all these stories, they'll always be limping. Now, from our side, we've been building up these black hole solitons, which differ from the black hole at the horizon. For extremal and for near-extremal, we have a mechanism. It's a mechanism which involves, again, topology, fluxes, brane polarization on abelian effects. That's basically this is the meat of this mechanism. And you can say maybe this is the only mechanism which string theory has. I don't know. But the point is, could one actually use these information theory arguments? Could one actually use these generic arguments to find the mechanism for extremal, for far away from extremality, to find a mechanism for Schwarzschild, or maybe find another one. I don't know. But this is really what I'd like to get some information. Again, I'm not very handy with these arguments. For me, it's all out there in the moduli space. But essentially, if I could get out of those arguments some mechanism, some way to give me some mechanism to go to the horizon, I'd be very happy.
So really, in the extremal case, the mechanism is force balance, right? It's the usual BPS.
It's not force balance. No, it's not force balance. If you look at M2 branes and you put them, next to each other on the Coulomb branch, that has force balance. But the moment you put one tiny perturbation on that, it just flushes and becomes the black hole.
So
the mechanism is really fluxes on cycles, and when you have
yeah, but those produce charges, as you were saying.
Yes.
And so in the end, it's a generalized version of force balance.
It's not force balance again. It's actually fluxes on cycles. When you have a flux on a cycle, if the cycle wants to collapse into a black hole, the flux says, don't do that to me, because the flux is quantized. You have, n units of flux. The moment you make the metric of that cycle very small, G with the legs up starts becoming big, and this flux gives you an infinite energy. So it's really the fact that you have bubbles and fluxes which don't want to be compressed. Bubbles and fluxes don't want to be compressed. That's really the mechanism. And that's why this survives, putting anti-branes. If you want to put anti-branes on, on Coulomb branch, distributed them to branes and so on and so forth, they just go in and, completely annihilate. The whole metastability comes because you have this bubble, you have this bubble, you have flux on it, and it's like a balloon. If it becomes a bit smaller, the flux says, hey, I'm having too much energy, I want to expand. If it becomes too big, then gravity says, hey, I want to collapse. And there's a balance between gravity, which wants to pull things together, and the flux, which wants to keep things out, which really works out and give these things to be horizon sized. That's the story for the BPS and for the near BPS.
Yeah, I just want to make a comment. I think that's very well put. I think that's a very good description of why they are stable. And just to emphasize that, the spectrum of vibrations of these is discrete. Exactly as saying, if you have a bubble, it's a stable potential well, right? It pulses rather than. So you can compute the vibration spectrum. And that matches the spectrum of excitation of the corresponding CFT state in the simple cases where you can identify the state. So there's a discrete spectrum, while if we just force balance, it's a continuous part of a continuous spectrum. It can just, if on the Coulomb branch, it can just drift. Yeah, so it's not that Coulomb branch.
Of course, if you look at superstrata, which depend on arbitrary shape, they look classically to have a continuous spectrum, because again, a superstratum can have any shape it wants, so I just touch it a tiny bit and it just changes shape. However, when you quantize it, you actually get that you cannot really have any shape you want. I mean, essentially different shapes correspond to different mode carriers, and so quantum mechanically, it's more like a quantum, to go from one state to the other one. It's not something which you see, classically you can put any shape you want, so it looks like the mass gap is 0, but actually once you quantize, you find that the mass gap is finite. But that's again something which you need to build. We need to build a superstratum, look at the solution, and compute this mass gap. Of course, and that's on the list of things to do to understand what the mechanism is. But again, the main hope which I have is, can one actually find a similar mechanism? Can one confirm the mechanism? Can one find something or find another one? So a few questions. Everybody keeps on asking. Okay, we're doing classical solutions. Would all the microstates be classical? Do you expect, we're doing classical solutions. Why do you do that? Why wouldn't the black hole be highly quantum, fuzzy, and so on and so forth? And, this is one of the reasons why Samir came up with the name fuzzball to begin with. Those are just, classical solutions, but, you expect the black hole typical state to be some, highly quantum, fuzzy thing. The point is the classical solutions are the only thing which I can do, honestly. I cannot quantize string theory on, like, some strongly curved, wildly fluctuating, quantum mess. I just cannot do that. I cannot find the string theory solution like that. I cannot find the spectrum. I cannot do anything. So my only way to get to this problem, which is again a very complicated problem, is to look at classical solutions and construct them, and then find the mechanism. And then once you find the mechanism actually extrapolates. It's exactly like in LLM. In LLM you have bubbling solutions. When you have the bubbles becoming very small and Planckian, you can actually replace the bubbles by a D-brane which is polarized. And you get exactly the same physics by just looking at polarized D-branes. And then if you actually turn the parameters differently, and you go to the regime when the D-branes which polarize become very small, you can have a non-abelian degrees of freedom on the polarizing D-branes which actually take over. So even if you are in the classical regime and you have big bubbles and so on and so forth, you know what these things become when you go to the quantum regime. You know that bubbles which become very small, they can be described by D-branes which become very polarized D-branes which become very small, they can be described by non-abelian degrees of freedom on some other D-branes. That's basically this is the story. So once you have the mechanism, once you have this hovering mechanism, it extrapolates. It actually tells us, what the underlying mechanism will be, even for things which are Planckian and quantum. Of course, I cannot describe those things. And essentially, the only thing which you can get is to get the building blocks. I mean, we are getting the building blocks, and again, this is what I believe the building blocks are. There's another question into what Samir was saying, and the whole argument, what's happening when you have a collapsing shell? A collapsing shell forms a Schwarzschild black hole. The Schwarzschild black hole is nice and beautiful. There's a horizon. You fall, 5 minutes after. Do you see a horizon, or do you get burnt? And again, Samir and David had this argument that you have to tunnel into some other geometries, and there's a tunneling probability, and you'll have many states. You can tunnel into all of them, and so on and so forth. But there's a simpler setup where one can actually study this problem, which is to actually use a near-extremal collapsing shell. You just put some D-branes, which are again extremal, and then you put a tiny bit of energy on all of them, and then you have this D-brane shell collapsing. Of course, at some point it will become a black hole, and then one can actually compute the tunneling from the D-brane shell into a metastable supertube configuration. That's something which, again, you have two solutions which are both near-extremal. For example, when the metastable supertube tunnels, it becomes, one type of D-brane. When you have another tunneling from one side, so you can actually brane flux annihilate. If you think about brane flux annihilation, you can have some D-branes and some fluxes, and what you can do, you can nucleate out of nowhere, and then a brane wrapping the cycles with flux, and you can actually make some physical brane out of bubbles, and you can actually compute the tunneling amplitude. So this is something which people can do. I can imagine taking a 5-center bubbling solution and then computing the tunneling amplitude into a shell of D-branes falling in, and then I'll get a number. And then the number is going to be right or wrong. I mean, either the number goes like e to the minus s, and in which case, I declare victory, or the number goes like, e to the minus s times, the number of branes to some funny power, in which case I say, no, this doesn't work, this scenario doesn't work. This is an arena where one can actually compute these things, do an honest calculation, and compute, what's really happening to a collapsing shell, and essentially find out whether when you collapse the shell, do you form a black hole, and then, somehow you have magically from the future, junk coming and destroying your horizon and forming a firewall, or do you actually tunnel into a firewall right away? This is some place where one can compute. One can at least get an order of magnitude estimate from this tunneling. There's another question, people, we in Saclay, we have been spending the last few years arguing that, anti-branes in flux compactifications are bad. We're arguing that, these anti-branes, the moment you put them, they destroy flux compactifications. You cannot use them to uplift de Sitter. There's no de Sitter multiverse. And indeed, if you do D3 branes in Klebanov cluster, so far it's bad. So far we have been doing all this work. We have been, tried, 5 different ways to make any sense out of them. We tried to put a black hole around them. We tried many, many things. None of them works. So at this point, okay, the jury is still out there. We're still trying to figure out, whether these anti-branes are good or not. But essentially there are two options. If the anti-branes are bad in general, and this metastable configuration breaks down, and I don't have any metastable supertubes or near horizon microstates, then essentially you cannot use anti-branes to uplift de Sitter either, and therefore there's no de Sitter multiverse.
There are many leaps there.
Yes.
The last statement was a huge leap, even if you accepted the first.
Yeah. There's an uplift mechanism using anti-branes, which I think is the most common. Yeah, one. So the point is, that particular uplift mechanism doesn't work. Now, maybe there's another one, and maybe, but I think this one is the most generic one. At least my friends who do flux compactifications for a living tell me that this is the most generic uplift mechanism, and essentially if you want to get e to the 500, universes, this is what you need to use. This is something which works for every flux compactification. The other ones are very specific. They work for some and not for the others. But again, that's something which we can discuss. If it's good, then the multiverse is okay. But then we have this story that the black hole singularities are resolved backwards in time and so on. Another question, do we go splat at the horizon size or not? And again, I want to emphasize it's very important to ask such a questions to basically use actual solutions. I mean, you can use infinite density shells in membranes. You can put membranes carrying degrees of freedom on the horizon and so on and so forth. There's nobody to keep them. You cannot have the tooth fairy coming and keeping your membrane at the horizon. It will just collapse. So if you want to ask a question like that, one actually has to use these actual solutions. Now, if you use the solutions and the ones we are building, what we are finding is that the force, for example, fluctuates wildly. Between microstate 1 and microstate 2, you are getting huge force fluctuations. And essentially they have no intention to sail through. And again, I cannot imagine any way to get empty space from this kind of solution. They have polarized branes, they have big bubbles. I don't have any way to get empty space, and therefore I believe that classical solutions stop describing physics at the horizon. And again, I think some people in Ohio disagree with this, but that's again my point. So summary, I showed you that in string theory you can construct configurations which hover above the horizon. They have, there are 3 ways of thinking about them, but it's all the same way, but in different regimes of parameter. That's the mechanism why you can do it. In the BPS case, we have the microstates which are horizonless solutions. The low mass modes affect the horizon scale, and we can get the right entropy on the nose. For extremal, we have an extensive story. I didn't tell you anything about it. We just have a huge number of solutions which are extremal non-BPS. We can play with them and so on and so forth. And then for non-extremal, essentially we can do 2 things. We can go to near-extremal, and we have done this using metastable supertubes. There's another method by Denef, which is called the supergroup. And Denef takes this multi-center configuration and move them on the moduli space very slowly. And then he tries to argue that essentially they give you some things which have more mass and charge. But again, those are time dependent, so they'll Hawking radiate and they'll be very messy. Maybe this is a story. That's another mechanism. And then the question is, what's happening far from extremality? So far, in principle, once I showed that you can go backwards in time, there's no reason in principle why this shouldn't happen for far from extremality. And to do it, I need some solutions. There are some black folds, inverse scattering, numerics. I've been trying to talk to everybody and their brother to build just a few solutions. We have JMART, which seems to work, but we don't have anything systematic. And unless I have something systematic, it's hard to see what's happening. There's like this idea of Matur and Turton, but it's also time dependent and not back reactive. So any suggestions of how to go away from near extremality, would be more than welcome. Thanks.
Okay, Gary.
Okay, so I actually have a question for Samir, because the argument you gave for why infalling observers may not see a firewall had to do with this, thermodynamic argument in the ensemble at some temperature. It's equivalent to the thermal ensemble, which is the usual black hole, and everything was fine. But so Iosif raises this interesting question. At 0 temperature, if you're at the extreme BPS, extremal black hole, what is your story about? Do you go splat? I mean, do you see a firewall at 0 temperature?
Yeah, I don't see any particular difference in what I was saying with 0 temperature, except for the fact that I think the sewing of 2 sides to make a 0 temperature hole is a little weird, because I think there is no Einstein-Rosen bridge, I think people are telling me. So I haven't thought that much about the extremal case to try to sew it up on two sides, to use this Mulsanov-Van Ramstorm kind of argument. But I think the difference here is the following. As I was mentioning in my talk, we went through 4 iterations, right? 1 and 2 are old, but 3 was you actually find the fuzzball structure, so you get the information out. Iteration 4 is when you hit this fuzzball structure, the surface, does it actually behave like an ADS-CFT duality? Like, you can't go in, but the vibrations are such that they have a dual picture, or maybe it doesn't. So, you could always imagine hitting this concrete wall, and if it doesn't have the right dynamics, it wouldn't happen. I think my guess is that it does happen, but a priori somebody could say the dynamics of fuzzballs is such that it doesn't happen. I tried to advance reasons why it would, and I do think it does. But I think at iteration 3 we all agree that you need the fuzzballs and they are there. I think the point is iteration 4 is the only way I can see that you can have the interior of the hole, and it's a matter of fuzzball dynamics, and I've just given my reasons as to why it should be of the ADS-CFT kind. But there are lots of surfaces that behave like ADS-CFT, like D-branes, and there are lots like this wall which don't. So I think that's the difference.
Okay, so presumably you agree that you can embed these guys within ADS-CFT. Mm-hmm. And now the question is actually going back to some old work that you did. There's this transfer function you can write down from the boundary to the bulk. Mm-hmm. So is this the statement that this transfer function develops wild fluctuations as you start approaching the horizon at finite temperature?
The way I see it is the following. If you go on the boundary on a given microstate, there's no, the bulk dual basically has, some geometry with a cap. And if I look at the transfer function, I can compute it, and I can reconstruct the the bulk dual, which has smooth topology and everything else, smooth solutions with some topology, from just doing the transfer function on one particular microstate. So, and then I can do the same story for another microstate and for another one. So essentially, I can find on the boundary a set of states which span my Hilbert space. And if I take each and every one of those states, using this transfer function, I can reconstruct in the bulk, the whole thing with bubbles and stuff. That's my feeling. Now, if you ask what's happening with the transfer function if I apply it on some thermal state, which is going to be, coarse grain and average and so on, I would say it probably starts fluctuating. Because again, I have a basis of my Hilbert space. And in my basis of the Hilbert space, each and every basis vector corresponds to a different cap, to a different structure. Now, if I look at the random guy in the Hilbert space, which is going to be my typical state, that's going to be something where geometry 1 plus geometry 2 plus geometry 3, that something should break down.
Okay, good. So this is something one can actually check, right? Because you can take the transfer function and compute it in a thermal background at least, mm-hmm. and you can check what happens to it at the horizon. So Kyriakos and I we did this computation, and it is regular at the horizon. Nothing happens. You don't get wild fluctuations at the horizon. So mm-hmm. at least for a generic state, as long as you take you can choose some strange basis in which this happens, but if you take mm-hmm. some generic superposition, it looks like that should be smooth as you go towards the horizon. Then you can ask whether, if you really had a black hole, if you can describe the interior or not. But in this case, mm-hmm. you should be able to describe it. So the transfer function does look like it's smooth, and we can, you can check the fluctuations, and it's not large at the horizon.
I see.
I think.
Well, if that's the case, this would be, basically showing that you can get empty space out of wildly fluctuating, superposed M2 branes, superposed polarized branes and bubbles and stuff. Because again, the physical, the states which we build, at least in the extremal case and the near-extremal case, they're all, bubbles and topology and, fluxes or, otherwise, polarized D-branes, and they all are different. They all have different energy momentum tensors. If you go to the horizon scale, it's as different as it gets. Now, that's my basis of my Hilbert space. This is my Hilbert space basis. Now, if a random guy there, which comes from, again, geometry 1 and, brane polarization 2 and, non-abelian thing 3, if you just put them all together in a soup and you look at the random guy in the middle of nowhere, in the middle of the Hilbert space, that one gives you a smooth solution and with basically small fluctuations. This would be, pushing, in a sense where what Samir is saying, that, it would be showing that you can get, empty space out of, superposing, wildly fluctuating geometries. Again, that would be quite surprising. That would be, in my opinion, that would be surprising. But this is the kind of argument which I think that would do it.